So welcome everyone to the Science Society. It's a wonderful weekend since we have here today as a guest speaker Dr. Barak Shoshany. And it will be a really exciting topic, as you can see from the title of the room. And let me give you a little bit of background information. Dr. Barak Shoshany, he's a theoretical, mathematical, and computational physicist. He's an assistant professor of physics at Brock University in St. Catharines, Ontario. And he's also a lecturer of computational sciences at McMaster University in Hamilton, Ontario. And his researches focus on the nature of time and causality in general relativity and quantum mechanics, as well as symbolic and high-performance scientific computing. And he did his PhD in quantum gravity group at the Parameter Institute for Theoretical Physics and the University of Waterloo in Canada. And he did his master's also at the University of Waterloo, and he won several grants and awards for his research. And it's a great honor to have you here today. Thank you so much for taking the time. And Victoria, please go ahead and ask your questions.
Okay.
All right. Yeah, welcome, Dr. Shoshany. Thank you, Katarina, for the introduction. And excuse me, I'm inviting somebody up. It's been really interesting to learn about the different guests that we've had here and their connections, the different connections that people have to science. And so my question to you is, looking back through your life, is there a moment or an experience that you associate with providing a spark of curiosity, maybe a teacher or a relative or just something, an event in your life that developed into your personal interest in science?
I never actually thought about it. I guess when I was a kid, my dad used to get me all those books from the library about physics and math and biology and neuroscience and all kinds of cool stuff. So I guess that kind of built an interest in science in me. But I think I probably would have ended up doing science anyway, because it's just something that fits with my brain, I guess.
Yeah, I think I know what you mean. You just feel an affinity.
Yeah.
Yeah, and I'm sure the books also help to kindle, or maybe they just fed your interest and your interest was just there, it's just innate. So, as a follow-up question, can you describe the path that led you to your current research?
Well, I was doing my PhD in quantum gravity, as Katerina said, and it was a lot of fun. But I was thinking about how can I apply this just for fun as a side project. How can I apply all this knowledge I learned by doing quantum gravity, which is basically general relativity and quantum mechanics. You have to be an expert on both if you want to work in quantum gravity. So I said, okay, well, now that I understand these two theories very well, can I apply them to anything from science fiction, just kind of as a cool side project? And I started just reading the literature, and I was surprised, in fact, that there are a lot of papers about faster light travel and time travel. Um, a lot, let's say, compared to what I assumed, which would be zero. So, there's papers out there by very prominent physicists um, that talk about these things, and that talk about them in scientific terms using all the equations and all the technical concepts and so on. So I just became interested and started reading more and more about it. And eventually I decided, after I finished my PhD and I already had a paper published in this area, I decided, okay, well, maybe I want to work on this now, not as a side project, but as my main field of research.
And can I also squeeze in a quick question? When you mentioned science fiction, did you actually find, was there any specific kind of science fiction you actually liked, or when you were going down the science route, did you actually get annoyed with it?
That's a good question. I've become more and more annoyed with science fiction as I learn more
I knew
science.
it.
Especially faster than light travel and time travel are things that are very often used in science fiction. I mean, you can't have a science fiction story that happens in space without faster than light travel. So that's one thing. And then time travel is also something that is very popular. People love to include it in basically every single science fiction series that lasted more than a few seasons contain some kind of time travel subplot. Some of them are mainly about time travel, but it's just very annoying. We start to realize that none of that actually makes any sense. None of that is actually compatible with the physics that we use, that we know is correct.
That's brilliant. Thank you very much.
And I often, if you follow me on Twitter, I often, like when I watch something on like a TV series or a movie or something about time travel, I always just post a very annoyed tweet about, oh, they did time travel so wrong here. Explain why.
We have to check that out. Thank you very much.
Yeah, thank you so much for your answer and for the details you provided. It really is interesting, and it helps give a human aspect to the person who's presenting their research, and it's interesting to have a little bit of background. So with your talk, you're welcome to follow any format that you'd like to present your research, and then if you'd like to have a following question and answer, or you'd like to have the question and answer, drive the body of your talk, it's totally up to you. And so with that, the mic is yours.
Just a quick
Thanks.
question. Your Twitter
Yeah,
is actually not listed in your bio. What is your handle?
it's just at my name,
Thank you.
like my full
Got it.
name.
Thank you. Go ahead.
So again, thanks for inviting me. And I think the model for this talk would be kind of I have some stuff I want to talk about, but then if you have any questions about anything, feel free to interrupt me and ask. So I don't know how that would work on a technical level, but I guess Katarina will take care of that, or someone else will. So let me get started. So like I said, I'm going to talk about faster than light travel and time travel, not really from the science fiction point of view, but from the pure science point of view. And I guess we should start with some motivation. Like, why, first of all, why are these things maybe useful, and why is it useful to study them? So, of course, like I said before, any science fiction story that involves space, it has to include faster than light travel somehow. I mean, imagine that there's suddenly there's an attack on some planet, and then they send a message to some other planet that's maybe not even around a different star, maybe around even the same star, but just very far away, this message, let's say they send it to somewhere that's 1 light year away. This message is going to take 1 year to get there, and then it's going to take at least 1 year for help to actually come. So the help will arrive 2 years after the attack happened. Obviously, that doesn't really create a very interesting and enticing story. So, it's just much easier to assume that, yeah, we have some kind of way to communicate faster than light. We send this help message and it arrives instantaneously in this other planet. And then they have some kind of faster than light engine or like a warp drive or something like that. And the help can arrive within minutes, and that makes for very good action sequences that just wouldn't have happened otherwise. So in real life, we of course maybe wouldn't be calling for help in the way I just described, but we definitely want to be able to travel to other planets, maybe even settle them, and we want to do this in a reasonable time. So let's say that we want to travel to some exoplanet. Now, you can't just travel to any planet. It has to be a habitable planet, and there's not a lot of those. Let's say there's some planet you want to travel to that's 100 light years away. Now, the fastest spaceship ever built by humans is NASA's Parker Solar Probe, which at some point reached a speed of 130 kilometers per second. That is 0.04% of the speed of light. It's just a completely negligible amount of the speed of light. And what that means is if I was flying at that speed to this planet that is 100 light years away, it would take me approximately 230,000 years to get to that planet. So obviously that is not very feasible. Now you can say that, okay, maybe in the future, maybe the far future, we will have spaceships that can move very, very fast and in fact can move very close to the speed of light. In that case, there are now two different durations that we need to talk about. There is the amount of time the trip takes to someone that stayed on Earth and the amount of time it takes for someone who's on the spaceship. Because if the spaceship is traveling very close to the speed of light, it's going to take it around 100 years to travel 100 light years. So if I'm sitting on Earth, I will see that spaceship arriving at the other planet after 100 years. But people inside the spaceship will experience a relativistic effect that is called time dilation, and they will actually experience this as a very short time. How short depends how close you get to the speed of light. If you get close enough, you can make this trip of 100 years to be 1 day or something like that. Like it's up to you. It's how much energy you have to accelerate. And I'm skipping a lot of engineering difficulties here. I'm just assuming we have the technology, right? So it can take a day, and then you come back to Earth. It's been 2 days now for you, but on Earth it's been 200 years. So everyone you know is dead. Although I guess if it's far enough in the future, probably lifespans have increased, but it's not really feasible, even with, let's say, 1,000 years lifespan. You don't want to spend 20% of your life just traveling in a spaceship. And I'm not even talking about just traveling to a completely different galaxy. It can be millions or billions of light years away. So it's interesting that, yeah, colonizing other planets, if you can move fast enough, it's not actually a problem as long as you don't care about coming back. You can fly to any planet you want. If you have enough energy to reach a substantial fraction of the speed of light, it can take you as short as you want due to time dilation, and that solves that problem. But obviously, if we were able to travel faster than light, then the trip would take a short time, both for people on the spaceship and for people outside the spaceship, at rest on Earth or on the other planet. So that is much more useful. But by the way, any questions so far?
I actually do have a quick one, if that's okay.
Yeah.
So, when we're talking about approaching these higher speeds, what is the factor for acceleration? Because obviously, if it would take less than a day, that would be and almost imply no acceleration time or very little. What would be factoring into the acceleration to get up to these speeds that could make it lasting only a day or so?
Well, like I said, I'm not talking about engineering. Like I just put all the, let's say, practical stuff to the engineers to figure out. I'm just assuming that you can accelerate fast enough. Let's say approximately instantaneously. But of course, you can sit down and do the calculations and say, okay, if you don't want to exceed a few G's of acceleration because the human body cannot withstand that, then it's going to take you a substantial amount of time to accelerate to close to the speed of light. But if we're talking about sufficiently advanced technology, it doesn't seem to be an issue as long as you have enough energy to accelerate as fast as you want. Okay, I guess if there's no follow-up, I'll keep going. So, yeah, of course, there have been solutions discussed in science fiction that don't involve faster than light travel. I mean, practically speaking, I don't believe we're going to have the amount of energy necessary to accelerate a massive spaceship very close to the speed of light anytime in the next few hundred years at least. So there are easier solutions to shorten the trip, or at least to make it feasible. Of course, longer lifespan is one of them. Like if people will just live forever, then maybe 100 years trip isn't a big deal. But if humans stay in their current lifespan, then we can have a sleeper ship, for example. So everyone is in some kind of stasis or cryogenically frozen, and then the ship travels and it takes it as long as it takes, let's say a few hundred years, because it's not traveling at the speed of light, it's traveling as fast as it can. And then all those people are just, defrosted, and they have not experienced these hundreds of years that have passed. So that's one option. You can see it in some science fiction stories. And another option is a generation ship. which is a ship where people are not frozen. They just live their lives. They have kids. They die. Their kids have kids, and so on. And then after a few generations, you eventually get to the destination, but all the generations in between will never actually get to see the destination. I would say that this is probably among all those different ways to travel to other planets, to other solar systems, maybe the most feasible with technology that might be available in the next 100 years or so, but definitely not. I wouldn't want to just live the rest of my life on a spaceship so that one of my descendants after 1,000 years is going to see the destination. So all of these options are 100% realistic. They're all possible with sufficiently advanced technology. The only thing I'm not sure about is about faster than light travel. So as you know, and if you don't know, I'll tell you now, nothing can exceed the speed of light. In fact, nothing can even travel at the speed of light. Only light, or more generally, massless particles that make up light and maybe some other stuff, can travel at the speed of light. And in fact, they have to travel at the speed of light. They cannot travel any slower or any faster. They have to travel at the speed of light. But if you have mass, then you can travel at like 99.9999999% of the speed of light, but you can never reach the actual speed of light because no mass can be accelerated to the speed of light unless you have an infinite amount of energy, which of course you don't. This is just not physically possible. Doesn't matter how much advanced technology you have, you can't just make an infinite amount of energy. Any questions? Feel free to interrupt and ask questions if you have any.
I have a question if I could.
Yeah.
Hi, it's Jim here. Thanks, Dr. Shoshany, or Professor. I have a question about this time dilation. It sounded like you described it a little differently than I understood it. So, if you're traveling near the speed of light, let's say 95% of the speed of light, and let's say you're going to Alpha Centauri or Proxima, so it's a 4.4 light year travel. If you're going 95% of the speed of light, it's going to take you on the ship more than 4.4 light years to get there, obviously, because you're only traveling at 95%. But my understanding was that, what's that?
It's so that's the point, that for someone looking from Earth, it will take a bit more than 4.4 years. But for you, due to time dilation, will take a shorter time.
But does it actually take a shorter time? Because you're experiencing time. Aren't you still experiencing the same amount of time as light would take to get there? Or more than that, because you can't actually travel the speed of light?
Well, so, it's been, it's kind of a very unintuitive thing. But it is true that in Einstein's theory of relativity, and therefore in the real universe, because relativity describes the universe, different observers have different notions of time. And this can be proven experimentally. And people did experiments, and they showed that indeed that is how the universe works. So they didn't detect a huge difference, but they detected like a few nanosecond difference, and this difference becomes much larger the faster you travel.
Yeah, I understand that. I'm just trying to understand that it sounds like you're saying it takes a shorter amount of time for the astronauts, but to them, they are still experiencing time at this regular rate. It's just relative to observers on the Earth. They are experiencing time at their rate, but relative to each other, because this ship traveling near the speed of light is going to appear to them on Earth to be traveling much faster in a way, and so therefore more time passes on Earth to the observers on Earth. That's always the way I've heard it explained. So I'm not. It sounds like you're saying though that it would take less time to like some out because the clocks aren't actually running slower for the astronauts. It's just as those clocks are perceived relatively from observers on Earth. Is that not correct?
The faster you go, the less time you will experience.
So maybe it's maybe better to think about this in terms of length contraction. So length contraction is kind of the opposite effect, where the faster you travel, the shorter distances become. So the time dilation you feel is exactly the same as if you were traveling a shorter distance. So if you have, let's say, a length contraction factor of, I don't know, 4, then you will see the distances being just 1 light year instead of 4 light years. And you know that you're traveling closer to the speed of light, so then you know that for you on the spaceship, it's going to take just 1 year instead of 4 years. But the people back on Earth don't see this length contracted because they are not moving, and therefore they see you traveling the full 4 light years, and they deduce it takes you 4 years.
Thank you so much for taking questions. I'm concerned about your time and want to make sure that you're able to get through the body of your presentation. So so
Yeah,
maybe we'll let you carry on, and then after that, since we are so blessed with a really big stage, and thank everybody for coming up. Let's mic flash before, and then we'll call on you just so that we make sure that everyone is heard. And but Serena, I think you were going to share a question that had come from the audience from Francesca. And then we can pass it back to you, Dr. Shoshany.
sure.
Thank you. And thank you, Serena.
Oh, okay. Yeah. So one question is, what would a realistic time travel plot look like?
That's a good question, and by the end of this lecture, I hope you will understand the answer. But there are
Okay,
some things
great.
I need to talk about first.
Okay, so take us away.
That's an exciting answer.
So, okay, maybe in the interest of time, if you have questions, just write them down and ask me at the end. So, okay, I think we've established that faster than light travel is a good thing to have for interplanetary or interstellar or intergalactic travel. And of course, if you can travel faster than light, you probably can also communicate faster than light. So you can, communicate with people on this other solar system, and it's not going to take you 10 years between messages. Now, time travel, I don't think has really realistic applications like that. I mean, sure, it would be fun to travel back in time and see how things were in the past, or kill Hitler, or whatever people want to do when they travel back in time. But I wouldn't really put that under something practical, more as something just interesting and fun. But I also should say that this research is 100% theoretical, and I don't know how to travel faster than light or back in time. And people send me emails and they ask me if they can use my time machine to go back in time. So, this is all 100% theoretical. So then why study this earlier? Theoretically, like I said, I don't think even if we can travel faster than light or back in time, it's probably not going to happen in the next few thousand years. You know, these things, as far as we know right now, require very, very advanced technology, if they are even possible, which is also something that we are not clear on. So why study it theoretically? Well, it's because these things, faster than light travel and time travel, they are ways to violate causality. And time and causality, these are fundamental concepts in physics that we don't fully understand. I mean, we understand them well. I wouldn't say we don't understand them. Certainly, general relativity tells you all about the causal structure of space-time and how time works and how time looks different to different observers, like I explained before, and so on. So we understand all those things very well, but there are a lot of unanswered questions. And my hope is that by studying these topics, faster light travel and time travel, at the theoretical level, we can find maybe something new, something that we haven't realized before about the nature of time or about the nature of causality. So, there's maybe the biggest issue comes from trying to combine relativity and quantum mechanics into a theory of quantum gravity, and I'm not going to go into that because that's not really the topic. But certainly that kind of messes up time in some ways. So we need to understand better how time works, and if we find, for example, that time travel is not possible, like let's say that I was able to prove time travel is not possible, well, that teaches us something about time. It teaches us that there are some mechanisms preventing time travel. And in order to prove it's not possible, one would need to actually develop new techniques and actually understand time better in order to prove that. So that's one thing you can do, or you can maybe prove that time travel is possible, which of course would also obviously tell us a lot of new things we didn't know before about how time works. Just working on the problem of figuring out if time travel is possible or not by itself already expands our knowledge about time. So I don't plan to build a time machine, but I do believe that this direction of research that I'm working on and that other people are also working on is going to reveal some interesting things. Or not, maybe not. But
That's exactly what a
maybe
person who's building a time machine would say. They would say they're not building a time machine.
yes. But anyway, let's get started on how faster than light travel would actually work, or what are the mechanisms that we have right now, the very theoretical and speculative mechanisms. And I'm going to start by talking about the expansion of the universe. So, as you may know, our universe is expanding. It started expanding 13.8 billion years ago at the Big Bang and has been expanding since. In fact, it has been accelerating the rate of its expansion. But what does that mean, that the universe is expanding? It means, and this of course is a very big misconception that physicists often encounter, when we say the universe is expanding, what actually happens is things are not actually moving. What happens is that space itself is expanding. So we know that space is expanding because we look around us in all directions, and everywhere we look, we see galaxies that are moving away from us. So there's, I guess, two possible explanations. Either they are actually moving away from us, which means we're the center of the universe. So that's probably not true, because there's no reason to assume that just because that we are the center of the universe, but no one else is. That is at least a principle in cosmology that people go by. Like, we are not special. Everyone in the universe has their own point of view, so we can't be the center of the universe. What is the other explanation? Well, space itself is expanding. These galaxies are not moving away from us. The galaxies are actually staying in the same place, but the space between us and the galaxies is expanding. And if you think about it, if that happens, then any galaxy would see all the other galaxies move away from it. So we see everyone move away from us, but then some other alien species on a faraway galaxy, they would see everyone moving away from them, because space expands everywhere at the same rate. So that is the explanation for this observation, and of course has been tested in lots of different ways, and we believe that it is true that space itself is in fact expanding. And why am I telling you all this? Because the fact that space itself can expand is actually, it presents a loophole that you can take advantage of. Because, okay, before I said nothing can travel faster than light, or even at the speed of light if it has mass. But the more precise statement is that nothing can travel faster than the speed of light within space. So if space itself is doing something, expanding or moving, then you can travel effectively faster than light. So what do I mean by that? Let's think about a galaxy that is very, very far away. A galaxy that is at basically the edge of the observable universe, and then think about a galaxy that's even beyond that galaxy. Now, the expansion of the universe, as far as we can see, it is uniform, happening the same everywhere. So we can easily calculate the velocity in which each galaxy is moving away from us using this very simple equation called Hubble's law, which says the velocity is equal to the distance times some constant. In other words, if you know the distance to the galaxy, you know how fast it's moving away from you. And if a galaxy is far enough from us, let's say around 14 billion light years away, then it is actually moving faster than light according to this equation. So does that break the rule that you can't move faster than light? No, because like I said before, the galaxy itself is not moving. The galaxy is just staying in place, and space between us and the galaxy is expanding. So this galaxy is effectively moving faster than light, because if we look at it, it will appear to be moving faster than light, but it's not actually moving within space. It's just the space between us is expanding, and that is a big difference. And this is a very interesting loophole, that you can take advantage of to build something called a warp drive. And of course, this concept exists in science fiction, like Star Trek, for example. And indeed, this is where the name was taken, is from Star Trek, for this actual mathematical equation or mathematical model that describes how to move faster than light using a warp drive by taking advantage of this loophole, which means if you can expand space at will, like you have a way to expand space and contract space, then you can build something called a warp bubble, and the space behind this bubble is going to expand, so it's effectively going to push you forward, and then space ahead of the bubble is going to contract, so it's effectively going to pull you forward. But then they both cancel each other, so then if you're outside the bubble, space is just normal space. So what happens is that you are just sitting inside the bubble at rest, not moving, not doing anything, and then the bubble itself, so kind of a small patch, a small region of space is actually moving. And there is no limit whatsoever on how fast space itself can move. So you are not moving at all. You're not traveling faster than light in your own bubble, but this bubble itself can move faster than light. Or at least that is the theory. Now it's interesting to note that this expansion behind the bubble and contraction ahead of the bubble is something that you will always hear when people talk about this warp drive, but in fact there are other types of warp drives that people have come up with that don't actually need any expansion or contraction. So the first one is called the Alcubierre warp drive, because the person who created this model is called Alcubierre, and then there's other warp drives like the Natalier warp drive, for example, that in that case there's no expansion or contraction. It's just basically just a bubble moving, just space moving on its own with nothing seemingly pushing or pulling it, which is even weirder than the usual warp drive. But anyway, so this is one way to travel. Is it feasible? I'm going to get to that in a second, but before that, I also want to tell you about another way to travel faster than light, which is maybe easier to explain because everyone already knows about it, which is wormholes. So if you had a wormhole connecting some portion in space to another portion, let's say between here and some distant star, then this wormhole can be much shorter on the inside than on the outside. So let's say the distance to the star is 100 light years, but the wormhole is kind of a shortcut that's only like 1 kilometer long. And you can just travel through the wormhole and you are immediately on the other side. And that I'm sure everyone here has seen before. It's also very popular in science fiction. But again, is it feasible? Well, there are many different reasons why these two things I just described, warp drives and wormhole, are not feasible. And one of them is that they both require, in order to create them, matter that has negative energy. So matter that we know of has positive energy, like you and the chair you're sitting on, or anything around you right now has positive energy. But if you want to build a warp drive or a wormhole, you need to have something with negative energy. We do know that there are some ways to achieve negative energy using some quantum effects. Well, I'm not going to go too much into details, but the basic idea is kind of like, okay, you have some kind of uncertainty, so you're not really sure if the energy is positive or negative, and therefore it can effectively be negative for a while. That sounds like just a ridiculous concept, but it is something you can actually do. People have derived equations and, in fact, inequalities that tell you exactly how much negative energy you can steal in this way. So, negative energy is not something that is completely impossible, but we do know, based on these equations people have derived, that you can create matter with negative energy, also known as exotic matter, but only at very, very small amounts and for a very, very short time. Definitely not in large enough amounts to create a usable warp drive or wormhole, or for enough time to actually travel in this warp drive or wormhole. No one has actually proven, though, that this is impossible. It's just that if you try to do it in this particular way, it's not going to be enough. But no one has proven that it is impossible to obtain exotic matter in some other way. So this is an open question. Also, no one has proven that you have to have exotic matter to travel faster than light. We only know that these two particular methods of traveling faster than light, warp drives and wormholes, they seem to require exotic matter, but maybe there's other ways to travel faster than light we just haven't figured out yet that don't require exotic matter. So it's this is, I think, is one of the biggest problems, because if I wanted to build a warp drive or a wormhole right now, I wouldn't be able to do it. I don't have the right. It's not that I don't have the right technology. It's that I don't even know where to start. Like, I don't even know where I would actually get this material I need in order to build it. Now, there's other problems. And again, I don't have time to go into it in detail. But for example, in warp drive, because it's traveling faster than light and you are at rest inside the bubble, you can't actually control where it's going, so you kind of had to place it in advance. But then if you place it in advance, well, that means that you were traveling faster than light before, so that you could place it. So I'm not sure how that would work exactly. And in terms of wormholes, wormholes connect 2 points. Even if I had unlimited amounts of exotic matter needed to create any wormhole I want, I have no idea how to make a wormhole that connects 2 specific points. I mean, you can mathematically talk about a wormhole that connects 2 specific points. I can write you these equations right now, but these equations describe a space that has a hole in it. How do you create that hole, and how do you make the other side of the hole be somewhere else? No one knows about it. I've never even seen anyone seriously talk about it. It's just such a hard problem that it's really not something we can really talk about in any educated way at the moment with the knowledge we have. However, there have been some suggestions that maybe these kind of holes in space can arise in the very early universe due to what's called quantum fluctuations. And then, so you have kind of like a microscopic wormhole, but then after 13.8 billion years of expansion, this wormhole is now several hundreds of light years long. So, maybe we can't build a wormhole, but we can use one that's already there because it was just randomly created after the Big Bang. So, in conclusion about faster than light travel, we kind of understand these two specific ways to do it within the theory of general relativity. So, it's not like someone just said, oh, maybe I'll build warp drive. It's actual precise equations that people have written and have studied in many different papers. But these are just equations on a paper, and we don't know if they correspond to anything that you can actually build or that can actually exist in real life. So this is an open question. It's a very open field of research. And maybe that's why it's so interesting, is because, trying to understand if these things that belong in science fiction and seem to maybe be compatible with physics of the real world, can they actually exist or not? It's a question I would like to answer, at least. So let me now move on to time travel. Now, what's interesting is that the way that we know, again, in terms of relativity, in terms of like actual physics, actual equations that are consistent with everything that we know, the way we know to travel back in time essentially is based on traveling faster than light. So if you can travel faster than light, and you can travel fast enough, faster than light, then you can kind of arrange things such that you can actually also travel back in time. And I do have a talk on YouTube where I explain this in more details, so you're welcome to look that up. I can't really do it now because I would need to draw something or to show you some kind of simulation, and it's not really something I can do in audio format. But essentially, it just takes advantage of another loophole in relativity, which says that if you can move faster than light, then you can move basically to another frame of reference where the future of that frame is in the past of the frame you came from. And therefore, now that you're in this other frame, you travel to the future and you end up in the past of the frame that you came from. So again, look up that YouTube talk if you want to see. I demonstrate that with a simulation in that talk.
I have pasted the link, Doctor, in the room chat, so if anyone's interested, you can find the link to that talk there.
Okay, great. So okay, if you have a warp drive, you can travel faster than light to do this trick that I talked about and travel back in time. If you have a wormhole, there's also a way to just turn the wormhole into a time machine by taking advantage of the thing I mentioned in the beginning of the lecture, which is time dilation. So you kind of make the time of one side of the hole be faster than the time of the other side, effectively making it into a time machine. So again, the question of is time travel possible relies on is faster than light travel possible? And by answering this question, we would also know if time travel could be possible. However, there are additional problems that come up when you travel in time that don't exist when you travel faster than light. And these are called time travel paradoxes. So it is entirely possible that you can travel faster than light in our universe, but you can't travel back in time, and you can't take advantage of this faster than light travel to travel back in time because it would create paradoxes. And what are these paradoxes? Well, everyone here has probably seen some kind of movie where there was some kind of paradox. There are two main types of paradoxes that are discussed in the literature. The first is called a Bootstrap Paradox, and this is a paradox where something is basically created out of nothing, or equivalently, where something causes itself. So let me give you an example. Let's say that suddenly a time machine appears and a future me comes out of the time machine and gives me a USB stick with the plans for the time machine. And then I use these plans to build a time machine. And then I go back in time to give myself the plans because I want to make everything consistent. So, okay, everything is consistent because I know that I showed up in the past, and indeed I came back to the past, and I recreated that event. But something here, namely the plans for the time machine, was created out of nothing because I didn't make those plans. And future me also didn't make those plans because future me is me. So if I didn't make these plans, I just got them from myself, who actually made them. Now, this paradox, honestly, I'm not too concerned about it because this situation I just described, it is a made-up situation. Like, how would such a situation actually happen even if you had a time machine, right? This is why I don't think it's really a problem, because for this to happen, then something has to actually be created out of nothing, because otherwise this wouldn't happen. So we can throw this type of paradoxes aside for the moment, and the type of paradoxes that is much more concerning is consistency paradoxes. And these are paradoxes where something happens if and only if that same thing doesn't happen. And of course, the most famous example is the grandfather paradox. But let me give you just an example without killing any grandfathers. So let's say that I step into my time machine, I go back 5 minutes to the past, and then I destroy the time machine. So now I can't go into the time machine and go 5 minutes to the past and destroy the time machine. So then it's not destroyed. But then if it's not destroyed, then I can go into the time machine, and so on and so forth. So you see here that me destroying the time machine is possible if and only if the time machine has not been destroyed. Hence, there is an inconsistency here. And this is a lot more concerning, because if I had a time machine, I wouldn't be able to create the other type of paradox, the Bootstrap Paradox, because I can't go back and give myself the plans unless I actually made the plans. But if I had a time machine, I could very easily create a consistency paradox. All I need to do is go into the time machine, go 5 minutes to the past, and destroy the time machine. Right? It seems like something that I should be able to do. But if I do it, it causes a paradox. Now, at this point, it's important to stress what I mean by paradox. Because in science fiction, usually paradox is something you can create. So, in Back to the Future, he goes back in time and somehow prevents his parents from meeting. Honestly, I haven't watched it in like 20 years. I don't remember the exact plot, but he prevents his parents from meeting, and then he looks at the photo, and his parents are fading out of the photo. So he kind of created a paradox, or is about to create a paradox, and he needs to fix it before, well, I don't know before what, but that is the general situation where you see in science fiction, is that someone just creates a paradox, and then maybe people disappear from photos, or maybe in the more extreme situation, they tear the fabric of space-time or something like that. But that is not what a paradox is to a physicist. If you are a theoretical physicist, what the paradox is something that indicates that your theory is incomplete, that the theory has problems in it. Because my theory, if it has paradoxes within it, if it has consistency paradox within it, then my theory is inconsistent. So it's not that I'm afraid that I could go back and create a paradox. It's just that it is impossible for time travel to exist if paradoxes can be created by time travel, because that would make the theory itself inconsistent. Therefore, the theory is incorrect. And therefore, if the theory is that time travel is possible, then the theory must be incorrect. So how do we resolve this? There have been a few suggestions. Stephen Hawking, of course, had his famous Hawking chronology protection conjecture, which basically says that the universe should not allow time travel to happen. So the universe protects the chronology, and that's all well and good, but you have to actually prove that this happens. So people have been trying to prove this conjecture, and the way that you can try to do it is you can try to take some kind of mathematical model that describes the time machine, and try to find some way in which this time machine would maybe collapse after a fraction of a second, so you can't actually use it, or maybe it's just not physically possible because there's some kind of a quantity that needs to be infinite in order to make this time machine. So, you try to find something not physical in this particular model. And people have actually found things like that in some very specific models, but no one has proven that this is true for any time machine, only for the specific time machines people have looked at, which are not the only ones that exist. Of course, the problem with this conjecture is it just makes the universe boring. So, it just means that you can never travel back in time, and that's it. So, maybe it's true, maybe it's not, but if it is true, the universe is maybe less interesting than it could be. So what else is possible? Well, there's another conjecture called the Novikov self-consistency conjecture. And this conjecture says, essentially, that the universe must be consistent no matter what. it's phrased in some more technical terms that I'm not going to go into, but essentially, the the idea is that, yeah, you could go back in time, but if you go back in time, you have always gone back in time. And then that means that you can't change things because things are already as they were when you did travel back in time. And I know that this is very confusing, and I didn't even understand what I just said, but that is what the conjecture says, is that you can go back in time, but you can never change anything. Of course, this also makes the universe very boring, but people thought that they have proved this conjecture could be possible, could maybe apply to our universe in a specific model of a particle traveling back in time. They showed, so basically, imagine a billiard ball. This billiard ball is going into a time machine. When it comes out of the time machine, it collides with itself and just knocks it out of the path into the time machine. So now it doesn't go into the time machine. So this is a very simple model of a paradox, a consistency paradox, because the ball, if it went in the time machine, then it knocks itself out of the way, then it doesn't go into the time machine. But then if it doesn't go into the time machine, then it does go into the time machine because nothing was able to knock it out of its path. So it's really the same thing as me destroying the time machine 5 minutes in the past. But this particular scenario can be resolved because you can send this billiard ball in a specific angle such that when it comes back out of the time machine and knocks itself away from its original path, the new path is actually going to be the path that brings it into the time machine, and now everything is 100% consistent. Again, this is something where visualizations might be useful, and you can take a look at one of my papers called Time Travel Paradoxes and Multiple Histories to see some visualization of that. But the basic idea is that in that particular scenario, it seems like the ball can go back in time, but it can't make any changes, and everything is consistent. If we want to talk about humans going back in time, which is usually the more intuitive thing to talk about, then basically I go back and I try to destroy the time machine, but I fail. How do I fail? Maybe I don't know, I take a hammer and I try to destroy it with the hammer, but the hammer breaks as soon as I do that. Or maybe I just don't have free will and I go back in time and then I say, okay, you know what? I'm just not going to destroy the time machine, and then everything is fine. So this seems to me a bit weird. It basically means that some things are just not possible that should be physically possible. Like, let's say I don't need to destroy the time machine. Let's say that there's just a self-destruct button on the time machine. I go back in time, I press that button, the machine is destroyed. Well, pressing a button isn't something that hard, right? I should be able to physically press the button. But Novikov's conjecture says that either I won't be able to press the button, or I press the button, but the mechanism is just going to break and it's not actually going to destroy the time machine. So, it kind of requires this very weird concept, which is that there's some things that are physically possible, but you can try as much as you want, you're never going to be able to do them. But maybe the most important issue with this conjecture is that it has actually been proven there are cases where it doesn't work. And if there's even one situation, one physically reasonable situation where this conjecture doesn't work, then that means this conjecture can't be true, right? Because if you want to prove something is true, you have to prove it is true in every single case. But if you want to prove something is not true, all you need is to show there's one case where it is not true. So in the same paper I just mentioned, you can see an example of a very similar situation to the one with the billiard ball, where there's just no way for this conjecture to be possible. There's just no consistent way for things to evolve. And therefore, there's a paradox in that particular case that just cannot be resolved using this conjecture. So now, I'm convinced by this example, unless someone shows me that Novikov's conjecture can actually apply to this particular case, but my student and I, who worked on this paper, we basically proved that it's impossible to find any consistent way for this case to exist. So what can prevent the paradoxes in that particular scenario? Well, if you assume there are multiple histories or parallel timelines, or however you want to call it, then you can just say, okay, I go back in time, 5 minutes to the past, I destroy the time machine, but the past I went to, it's a different timeline. So when I step out of the time machine, the history of the universe splits into two. And now there's two different futures of that point in time. The first future is the future where the machine is intact and I go into the time machine. And then the other future, the one that was now created, is the future where I destroy the time machine and now the time machine is not intact, so then no one goes into the time machine. But there's no paradox here, because the me going into the time machine is now no longer dependent on me not destroying the time machine. So there's just two different timelines, one where the machine works and I go in, one where the machine is destroyed and I don't go in, and they're just completely independent, so there's no paradoxes here. You can apply this, in fact, to any time travel paradox that ever existed. There's no paradoxes that it cannot solve, while there are paradoxes that the Novikov conjecture cannot solve. Therefore, it seems like if time travel was possible, then it must also be possible to have multiple histories or parallel timelines. So now you can ask, well, okay, but do we have parallel timelines? Is this a physical possibility? And that's a good question, and that is a question that I'm also working on with a few of my students. There is, of course, the quantum interpretation, known as the Everett interpretation, and also known as the many worlds interpretation, where essentially when you make any kind of measurement, the universe basically splits into different parallel universes, one for each of the outcomes of your measurement. So when I say measurement, I mean really anything, any kind of event that happens that can happen in more than one way. The the usual example is the spin of an electron. So an electron can spin, let's say it can spin clockwise or counterclockwise. And when I measure the direction of spin, then I split into two, one version of me in one history or one timeline or one universe measures the clockwise spin, and the other version of me measures the counterclockwise spin. It's not actually clockwise and counterclockwise, it's kind of more complicated than that, but I find that this is the simplest way to explain what a spin is. So, is this something that actually happens? Do I actually split into two? No one knows, because there's no way to test it. It's just a philosophical interpretation. So it could be that it is true. And personally, I find it to be one of the more attractive interpretations, because it doesn't actually introduce any additional things on top of quantum mechanics. It's really just pure quantum mechanics. But there's also other interpretations that also work. So if this interpretation is true, and there is an actual physical existence to these other timelines, these other possible measurements, then you can just say, okay, well, let's measure if I arrive back in the past or not, and if I do, then that's going to be a different branch of the timeline. So all of this is just words. This needs to be done mathematically, but I think it can be done mathematically. It's just that no one has done it yet. There may also be other ways, without using quantum mechanics, to have a universe that can accommodate different histories or different timelines happening simultaneously. And I'm not going to go into that because now it starts to become very technical, but this is an open question that some people are working on, including me. And the goal is, if you can find a concrete mathematical model, if you can find a theory of physics that allows these parallel timelines to exist, then you haven't proven that the time travel is possible. Let's be clear about that. This doesn't prove time travel possible, but it means that you showed that time travel is not impossible due to paradoxes. It may be impossible due to other stuff, but not due to paradoxes, because these are presumably resolved by these parallel timelines. Yeah, so I have lots of other stuff to talk about, but I think I've talked for enough time. So I want to thank everyone for listening, and maybe let's open it up for questions.
Yeah, thank you so much for this amazing talk. I mean, everyone has been very excited about your talk and this topic, so I really appreciate it. And may I ask you a very uneducated imagination I had like years ago when I read about parallel universes and entropy and so on. The idea I came up with for a kid's book Time Travel was that you basically use the parallel universe as a entropy dump, like trash can. So you basically have an AC entropy AC that would locally decrease entropy and then have some sort of time travel. Would that be ever possible? Like, would it be an enclosed system then if you would be able to connect to universes that ideally go in opposing time? lines?
Well, that's a very interesting question. I think this question has a hidden assumption, which is that entropy and time are actually things that are intimately related, and that if somehow you could decrease entropy, then you automatically go back in time. However, that's not true. That's not how it works. So the second law of thermodynamics says that statistically speaking, entropy has an extremely high probability to increase over time, but it doesn't have to. There's a very, very small chance that entropy actually decreases. And of course, you can decrease entropy in one place if you increase it in some other place. So the thing is that even if you were able to decrease entropy, that wouldn't actually move you back in time. It would just decrease the disorder of a particular system, or even the disorder in the whole universe, because that's what entropy is. It's a measure of disorder, but it's not going to turn back time.
So it's not a rejuvenation for our universe, basically. It wouldn't work that way to rejuvenate our universe.
You could rejuvenate the universe. So the problem with entropy is that as entropy increases, the amount of work you can do, and work in physics means really just any kind of transfer of energy, any kind of taking energy and making something useful out of it. The amount of energy that is available to do that decreases when entropy increases. So eventually, the universe is going to reach a state of maximum entropy where nothing can happen anymore. There can be no stars, no life, no physical processes, because there's just no energy that can be used to power any stars or any life. And then if you can do what you said and just dump all this entropy into some other universe somehow and decrease the entropy of our universe, then you could rejuvenate it and maybe start creating some more stars, creating some life, and so on. So that maybe is possible. I don't know, but it's
Thank
not
you.
going to take you back in time.
I will let other people ask questions, but thank you. I will tell that my son, he is very worried that our universe will die and we will all die. So this is a great answer. Serena, go ahead.
So yeah, I want to question. I want to take it back in the earlier part of the talk where you were talking about expansion of space and contraction, and within the license that there was even a term, the usual warp drive. So within that thinking space, the formalism of contracting space. Within that formalism, is it consistent to contract the space between the objects? And what I mean by that is there any particular shape, restrictions that come out of the formalism? Could you, in essence, expand and contract in two regions of space and rotate them past one another? Can you identify stars that have no interesting systems and contract the space between them and send them smashing into one another if you needed a bunch of energy? That kind of stuff. What, in terms of the formalism, would it look like to contract or expand space? Can you expand on that?
Yeah, I will expand or contract about it. So that's a very good question. And here's the thing: the warp drive is kind of cheating, because in relativity there's this equation called the Einstein equation, because Einstein came up with it, and then this equation tells you it has two sides. On one side, you have the curvature of space-time. So how space-time is curved and bent and expanded and contracted and so on. And then on the other side, you have what kind of matter corresponds to that. And now you can solve this equation in one of two ways. You can say, I have this kind of matter in this kind of configuration. I put that on the matter side of the equation, and then I find the curvature that this matter will create. But you can also do the opposite. You could say, I want space-time to have this specific curvature. And then you put that in the curvature side of the Einstein equation. And then on the other side, you'll find what kind of matter you need. So this is exactly why we find that we need this exotic matter that has negative energy, because we say, okay, I want a rope bubble. So, okay, I want expansion over here, I want contraction over here. Okay, I write it all down, I put it in this side of the equation, and then on the other side, I now have what kind of matter I need. And then this matter turns out has a negative energy density. So essentially, the answer to the question is you can do whatever you want to space-time if you have the right kind of matter, the one that solves the equation.
Interesting, thank you. So we could, bootstrap with the asteroid belts and bring Alpha Centauri closer eventually.
Well, the warp drive is just a tiny portion of space where there's some expansion and contraction, and it already requires enormous amounts of negative energy. I don't even want to think about how much energy it would require to contract a space between us and Alpha Centauri. It's probably more energy than in the entire observable universe. So that's probably not a feasible thing to do. It would actually be more feasible to literally just grab Alpha Centauri and just drag all those stars and planets over here. I think that would actually be more feasible than contracting space itself between us.
Well, thank you. Dr. Shah, I think you flashed your mic.
Yeah, thank you so much, Barak. That was fascinating. I mean, my question is about we know that about the post selection, and we know that it's impossible in a zero probability. However, you just talk about the Novikov conjecture and the small probabilities beside the quantum fluctuations. My question from you, I mean, do still based upon whatever result that you just explained to us, do we have an information paradox in this situation or not?
What do you mean by information paradox? You're talking about the one with
Yeah,
the
I mean
USB
that
stick?
information which they cannot destroy in a universe, because we have one theory about the how, I mean, how can that just explain about both of the black hole and evaporation of the information. However, the way that you just explained about the time machine, it just brought up this question to me. When we are talking about the quantum, I mean, fluctuations, what's going to happen to the information?
Um, I'm not sure exactly what kind of scenario you're talking about, because there is the black hole information paradox, which of course has already been solved. We just have like 1,000 different solutions to it, and we don't know which one is the correct one. But that's something that presumably happens in a black hole, because you can put information inside, but information presumably cannot get outside of it, and then it slowly shrinks until it just disappears after many, 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 many years. And then you ask, okay, well, where is all that information? And then there's like 1,000 different solutions where people say, oh, the information is here, the information is there, the information doesn't actually have to be conserved, and so on. So that's one thing, but I'm not 100% sure how it's related to time travel.
Yeah, I think that it needs more explanation. I prefer to back channel you. And people have time to ask you more further questions. Thank you so much.
Yeah, you can always just email me after this and we can discuss it in more details.
Kirko, you have a question? Please go ahead.
So super cool talk. Like I watch so much like random YouTube videos on like stuff like this. But I really don't know anything. But I was kind of curious, right? So like on the warp bubble that you're talking about, like if the you said like something like the rear end of the ship would be like expanding space where the front end space would be contracting. And like I was just kind of like super randomly curious. Like so if you contract the space, like wouldn't that contract what's in the space? And if so, could that like create like tiny black holes? You know what I'm saying?
Um, no, I mean, you don't create a black hole by contracting something. Um, you create a black hole by putting enough mass inside the small enough radius. But I don't think you need to actually compress that stuff within space. If you just compress space itself, then the radius is also going to be compressed. So then you didn't actually change anything. So you're not going to make more mass be within uh, the smaller radius because everything will be kind of uniformly compressed. What you need to create a black hole is you need to have space itself stay the same, and then all the mass move within space closer to uh, where you want the black hole to be. But that's a good question, though.
But space doesn't stay the same in the black hole. Space is warped in the black hole, right? But what about dark matter? Maybe he's right. Maybe that warp bubble will gather and compress dark matter into a black hole.
So, like I said, even if it compresses matter, and it doesn't have to be dark matter, it can be just cosmic dust. It can compress it. I don't think it can create a black hole. What it will create is it will create radiation that is going to destroy the spaceship. So, that's another issue that people are talking about. But I feel like that is kind of more like an engineering problem, not something that prevents the warp drive from being constructed, but just a problem that, okay, if you did construct a warp drive, how do you deal with this radiation that is going to create, that's going to destroy everything inside the warp drive, inside the bubble?
I have one more question if that's cool.
Yeah.
So like you guys said like say for example if you were to travel like close to the speed of light, like you would experience like time dilation. So I was curious like if you were to like travel like the same distance via a warp drive, would you still experience time dilation? Because like I don't know if you would technically be moving fast. You know what I'm saying? Like I don't know how that would
Yeah,
work.
yeah. That's a very good question, and a question that indeed has been asked by physicists before. And the answer is that since you are not moving, because remember, I said that the idea of the warp drive is that the bubble itself moves, but you are actually at rest in space. And then because you are not moving, you don't experience any time dilation.
That's super cool.
Yeah, please flash your mics if you have questions. A lot of people joined the stage, so please go ahead. Yep, Denise.
So Doctor, thank you so much for your presentation. I was curious about you had mentioned several times that there's no way to generate the energy that would be required to create this sort of travel. I was curious about the theoreticals of how much energy would be required.
Yeah, so this is something that it depends who you ask, because in the original paper by Alcubierre, the first paper on warp drive, I think it was something like you need all the energy in the known universe, but also it has to be negative. And then in other papers, people have been able to reduce this to like um, just the amount of energy in the planet Jupiter or something like that. But again, negative and not positive. So you can't actually take the planet Jupiter and convert it into energy because that's going to be a positive energy. I'm actually working right now with one of my students, and we are about to submit a paper soon where we actually show that in 5 dimensions you can make a warp drive using as little negative energy as you want. So you still have to have some amount of negative energy, but this amount can be like 10 to the minus 100 or something like that. Like you can just create a warp drive using a negligible amount of negative energy, but that depends on having an extra dimension, which may or may not be a thing.
Fascinating. Definitely looking forward to reading those papers.
Yeah, actually, that's a question I wanted to ask. But I guess you already mostly answered. But it does basically this you design the metric, but when you put it into the Einstein's energy the tensor field equation, you calculate the energy, but the is it always sorry the is it always true that no matter what the functional form of the metric is, if you have this kind of uh, drive, whatever you call it, warp drive or not, the energy will always be the field energy will always be the negative. Is it provable, or under what condition
So
is it true?
yeah, that's a good question. And so once you have the particular, you said metric, maybe other people don't know what the metric means, but basically once you have the particular curvature of spacetime you want, you check what kind of matter you need to make that curvature. So if you check that for the warp drive, you find that this matter has to have negative energy. If you check it for the wormhole, you also find it has to be negative energy. And that is true for basically every single warp drive and wormhole that people have considered, um, except ones that don't go faster than light. So it seems like there's something about traveling faster than light that somehow requires negative energy, but no one has proven that if that faster than light travel requires negative energy in general. They only proved that these particular ways of traveling faster than light require negative energy.
Well, so
Uh,
doesn't going faster than light, at least in some conceptions, implies um, not obeying the ordinary relationship between space and time. So therefore, doesn't going faster than light imply a certain kind of going back in time? And if so, doesn't that imply negative mass?
Okay, well, there's two two things, right? So yes, traveling faster than light does imply traveling back in time. And I talked about this a bit before. And there's a YouTube video where I explain that with some visualizations. But essentially, if you can travel faster than light and you can travel fast enough, so it's not enough just to travel faster than light. You have to travel at a certain speed. That, of course, depends on how far you want to go back in time. And yeah, you can use that to travel back in time, but that's just not, it's not related to negative energy or negative mass. It just means you travel back in time. So, you know, the reason we need negative energy is just that this is what the equation tells us, and now people are trying to understand why that is. But it's not related to traveling back in time, because it happens even if you don't travel back in time. If you just travel faster than light, but not back in time, you still need this exotic matter that has negative energy.
When you,
I, I,
I have a question.
Yeah.
When you go faster than the speed of sound, you create a sonic boom. Could there be sort of an analogous in your warp drive where you create gravitational waves or a gravitational boom when you're traveling faster than the speed of light?
Like a gravitational shockwave.
Yeah.
Yeah.
I'm not sure about that. But you know, there is a concept of Cherenkov radiation, which is radiation that is emitted when something travels faster than light in a medium. So there is this analog thing to a sonic boom. I don't know what happens if you travel faster than light in vacuum. This is what happens when you travel faster than light in a medium, which of course is possible, and that's why we know this radiation exists, because we can see it in, you know, like nuclear reactors and stuff like that. You can see this Cherenkov radiation. Maybe it will be created if you travel faster than light in vacuum without any medium. I'm not sure about gravitational waves. The thing about the warp drive is that the space-time outside the warp drive, outside the warp bubble, is completely flat. It's just space with no curvature whatsoever. And a gravitational wave is a wave in the curvature. So then if outside the bubble it's all flat, then there can be no gravitational waves. But I don't know, maybe the problem is that people just not considered this question before. And maybe you can.
I think that interaction between the warp bubble and a gravitational wave would be an important question to see if there's any stable solution.
Well, my point is the warp bubble would be traveling through the fabric of space. And
Well, no, so let me stress something important. The bubble is not traveling in space. The bubble is just a part of space. So this is why it can travel faster than light. So it's not that you're moving in space faster than light. It's that space itself is expanding in the same way that it's expanding between us and distant galaxies. And this expansion and contraction make it such that there's a portion of space that is effectively moving, but nothing is actually moving. You inside this bubble are just at rest, just sitting around, not doing anything, and space itself is moving.
well, my thought was that the expansion and the contraction is what is going to create that gravitational wave or gravitational boom.
Um,
well,
you know, I haven't studied this question in detail, but I don't think so, because gravitational waves are created in specific situations For example, if there's two black holes that collide or stuff like that, if you just expand space, that doesn't create gravitational waves. So I'm not sure if this does apply here, but it's a good question. It's something that maybe should be looked at.
Thank you, Dr.
What if
Shoshani. We really respect and appreciate your time so greatly. We want to double check with you because we're going on 2 hours now. And how much more time would you like to spend here? And that will guide our the remainder of Q&A, and totally up to you.
Yeah, I mean, we can do another 15 minutes or half an hour. Let's see if people still have questions in 15 minutes. And then
Okay, so we'll plan on ending for sure by what we have is I have 8:15. I'm on the West Coast, so yeah. Thank you so much. And then a quick room reset of the way we were doing this. We're so grateful to have such a large stage with so many friends here who are showing interest in Dr. Shoshani's work. So please, let's have mic flashing, and then we will call on you and make sure that everyone's questions get answered in that way. So if you would please flash your mics and have us call on you, and then go ahead. Thank you, Dr. Shoshani. Okay, I see Shane. Welcome to the stage. The mic is yours.
Thank you. So, I mean, my question isn't very technical, but I was curious if you've seen any examples in any kind of media that you think is the closest realistic example of time travel.
yeah, good question. So like I said, most, if not all, time travel in fiction suffers from this very big problem, which is there's just paradoxes that happen, and a paradox can't happen. A paradox is an indication that the theory is incorrect, right? So there's a lot of movies where you go back and you change something and then you have to fix it, because if you don't fix it, you create a paradox, and that's just nonsense. Like, I think one thing that you will notice in most time travel shows is that there's kind of like the timeline of the viewer, and things are somehow constructed by the timeline of the viewer. So like, you'll go back in time and change something, and then according to the viewer, there's some amount of time where you can still make changes and fix it. But of course, according to time itself, if you change something in the past, it doesn't like propagate slowly to the future. It actually just changes the entire future, because that's how time works. Time doesn't take time. So that's, I think, the number one mistake. And you see it in almost every single time travel, movie, TV series, book, comic book, whatever you want. There are some time travel stories which use Novikov's conjecture, which is kind of makes more sense. So they just say, okay, well, this change in the past happened, but actually that's how things have always been. And you as the viewer only realize that after the fact, that this actually already happened. It doesn't change the future. So this person went back and slept with his mother, and then he was born. That's weird, but it's consistent. So that's something that kind of makes more sense. But my issue with those kind of stories is that it, it's like you could create paradox if you wanted to. So like, a lot of the time you see someone, like, some event happens and then someone goes back in time and now they're the future person. So they say, oh, okay, I have to do exactly what I remember myself doing when I was in the past. And then they do the exact thing, and then presumably that doesn't create a paradox, except that's not how things work. Because if you then decide, oh, you know what, I'm just not doing it, I'm just gonna not do what I saw myself do, then you just create a paradox. And again, that doesn't make sense, but you see that a lot. And honestly, all those things I just described are basically all time travel stories ever written. I get asked this question a lot, and there's just no examples I can think of time travel that actually makes physical sense or makes logical sense in movies. But if I find something, I will definitely, um, let people know about it.
I'll just quickly comment that a solution that's a non-solution but would work would be lumping that into Everett's many universes hypothesis. But of course, that's a debated hypothesis.
Yeah, so I don't know if you were here before, but I did mention that as one possible solution, but it needs to be more than just words, right? So it needs to be some kind of concrete mathematical model, and so this is something that I'm, along with my students, trying to work on, but it's harder than it sounds. And I'm not the first person who thought about this. People have thought about this for decades, but no one has been able to make it work.
Thank you. I believe that next is Jamie. And Jamie, I think you have your question, and then also you're sharing a question from Victoria in the audience. Go
Yes,
ahead,
I am.
Jamie.
Thank you. Thank you, Victoria. Doctor, thank you so much for this talk. It is absolutely incredible. Okay, get to it anyway. In the earlier part of your talk, you mentioned wormholes. I don't know if you covered this or not, but uh, I was wondering if a wormhole could in any time be theoretically possible, would that be including like compressing space in one sort of small tunnel, like pulling it in or something to go through it to get to somewhere? Or were you talking about opening a wormhole from one end, punching out of the universe, to outside space, and then punching back in at a different point?
Yeah, so you can't really punch out of space because there's nothing out of space. Space is space. So
Yeah.
if we talk about the wormhole, we generally talk about 2 points in space that are somehow connected. And mathematically, it's very easy to do. You just say, okay, well, these 2 points are the same point, and that's it. Then you have a wormhole. But how do you do this in reality? No one knows. And I talked about this a bit before. Like, okay, I know if I had enough, let's say I had unlimited amounts of exotic matter and I could create any wormhole I wanted, the problem still remains, how do I make that whole? That whole is the thing that no one knows how to make. So that is really the problem. Now, if you had extra dimensions, if there were 5 dimensions of space-time instead of 4 dimensions, then you could perhaps go through this fifth dimension and use that to connect to some other point. But that wouldn't really be a wormhole. That would just be you moving in this additional dimension.
Right, that's fascinating. Okay, and the other one, this is a really good question from one of our audience members, Victoria. She was wondering if there was a big crunch at the end of the universe, if that means that at the end of the universe, all of the laws of, everything all break down, wouldn't that invalidate all of the theories of time travel?
Um, I don't see why. I mean, if the universe ends in a big crunch, that happens in trillions upon
Well,
trillions of years, but I can go to the
uh,
past now, and I'm not influenced by that big crunch.
But I think my thinking here was if everything's breaking down at any point in sort of the time span, would that mean that going through time, the effect of that would be
Well,
somehow
that's
affecting?
not what
Would there be an additional anomaly created as just by virtue of merely traveling through time, in addition to all the crazy things that happen with the equations? That's how I would interpret that question, if I may say so.
so.
Okay.
Okay, so if the big crunch happens, nothing is going to break down. The big crunch is part of physics that we know and understand. So the big crunch basically happens when the universe stops expanding and starts contracting. And it contracts and eventually contracts into a very, very small size, but that's not going to affect the past. That's something that's going to happen in the future, but the past is not going to be affected by it. And it's not going to break physics. It is part of known physics. So, it doesn't change. Uh, if I could travel back in time right now, then that's not going to be affected by the big crunch happening in many, many, many years in the far future.
I see. Thank you very, very much. An amazing talk, Doctor. Thank you.
No problem.
All right, thank you, Jamie. So next, I believe we have Lisa. Lisa, are you still here with us? Looks like Lisa is not.
No, yes,
Lisa!
sorry. Having trouble unmiking here.
Oh, there you are. Yay. Okay, the mic is yours. Thank you.
Yeah, thanks. So I have kind of two questions. One is just a general one. When we talk about paradox, I cannot help but think of Zeno's paradox, and I don't understand why it is so problematic for there to be a paradox, or it seems like paradoxes are a mainly human issue rather than a purely physical space-time kind of issue. And then the other, I'm curious, you mentioned just briefly that you could exceed light speed in a medium. And it seems to me that the cosmic microwave background radiation indicates that all of space-time is within a medium. And so I'm curious of your take on that.
So let's start from the first question. So Zeno's paradox is not a paradox. A lot of things that are called paradox, like someone's paradox, are usually not actual paradoxes. So Zeno's paradox is something that can be easily solved once you understand how math works. Therefore, it's not a paradox. Something that is truly a paradox is not a human problem. It is a problem of the theory itself. So, if my theory of time travel contains consistency paradoxes within it, that means that my theory is inconsistent and therefore cannot be correct. Because there is this basic logic that the universe has to satisfy just because it's something so basic. Like it's impossible to imagine a universe where things are actually just not consistent, right? There has to be some logic, some consistency to things. Otherwise, nothing means anything, right? So when you write a theory, sometimes there are issues with that theory that mean this theory cannot possibly be true, and time travel paradoxes are such an issue, and that's why they need to be resolved. But other paradoxes, like the Zeno's paradox or the twin paradox, these kind of things are called paradoxes, but they're not actual paradoxes. They're just like weird things that you need to think about. So that is for the first question. And for the second question, when we say light moving in a medium, we mean a specific thing. So, you have some kind of a medium, and there's a refractive index of light, and light is going to travel slower within that medium for some reasons that I'm not going to get into, but the cosmic microwave background is not a medium. The cosmic microwave background is light. It's just light from the very early universe. I think it's like 180,000 years after the Big Bang or something like that. And it is light moving through vacuum. So it's not an issue. It's not really a medium that light goes through. It is light.
Thank you. To reset the mic protocol, if anyone has a question, please flash your mics, and then we'll take note and call on you in order. Before that, I want to say that we have about 10 minutes left, so please keep questions brief. And I want to thank everyone for being here this evening. We are so happy to be able to provide a really great audience for Dr. Shoshany. It just makes it all the more fun, and all of your questions and comments make the room as wonderful as it is. We've had a very lively room chat tonight, and a lot of really great feelings and interest. And I see people are sharing books and things in there. So it's just so homey. Thank you, everyone, so much. Eric, I think that you might have a question. Otherwise, I see Carlos. Carlos, the mic is yours.
Maybe they went to the bathroom or something.
Yes, or can't reach
Yeah.
their phone.
Yeah, actually, I have a question with regards
Hanson,
to
you have a
the.
question? All right, Hanson, the
Yeah.
mic is yours.
Okay, thank you. The I was thinking about the this negativity of the energy. So it's basically a contraction, right? So is there anybody like looking at the general form of it? Uh, I suppose that not all the components are negative, but the sum is negative. And has anybody looked at it, and um, is it coming from, let's say, for example, I don't know, the compactness of this metric distortion or shape function that's constructed that is of finite radius. Is that the reason that it goes to a negative? I know that you said
Right. So
nobody has shown. Okay, go ahead.
yeah, I can answer what he said. So I mean, first of all, it's not a sum of anything. It's just a value at each point. So the part where there is negative energy, so where the matter at that point must have a negative amount of energy, that's actually not where you contract space. It's actually, if you imagine the bubble behind your expanding space, in front you're contracting space, both of these places you don't need negative energy. Where you do need negative energy is actually on the sides. So nothing actually seems to happen on the sides, but you need the matter with negative energy there. And if you read my paper that is quoted in this was like the title of this talk, then you can see it actually. I did a plot of the energy density, and you can see that it's interestingly not actually where you expand or contract space. It is to the sides. And now for the other thing you mentioned is I think maybe you're referring to this paper that I don't remember right now who wrote it, but there was a paper last year where basically they showed that the reason you need negative energy for specific types of warp drives is basically that uh, you need, if I remember correctly, basically the integral, or let's say the sum of the energy in all of space has to be zero, and for it to be zero, that means there have to be positive parts and negative parts. And I'm probably not remembering it 100% correctly, but that is something that they claimed in that paper. I'm not 100% sure it's true because there have been papers after that that said it's not true. So, like I said, it's still something people are still looking at.
I see. Great. Thank you very much.
Mhm.
Yeah. Okay. So yeah, originally when I say some, I was referring to the trace. But anyway, that you did answer the question of the it's on the side that that
If
requiring
you
the
want to
negative.
calculate if you want to calculate the energy density somewhere, you don't take the trace, you contract the stress tensor with two vectors, so you just get a number in the end.
Yeah. That's what I mean by trace and the summing the indices. But yeah.
Right. Yeah.
Fantastic exchange. Thank you, both of you. I see that Nick has a question. Nick, the mic is yours.
Hi, given the length of this, my question is extremely short, and I would accept yes or no answer. And of course, Dr. Shoshany, I missed your presentation, but my question is, um, when Feynman defines antimatter of, normal matter traveling backwards in time, you mean something entirely different than that when you say travel in time. Is this correct?
Right. Yes, but I should explain why. And the thing is that antimatter doesn't actually travel back in time. What you're referring to is just a kind of a notational convention. So when you draw these Feynman diagrams, then by convention, you draw the antimatter moving in the opposite direction in time, and there's a reason for that, but it's just a notation. It's just like you choose to write it that way for some reasons, but it's not actually moving back in time. It is still moving like everything else forward in time. You draw it in the other direction for some reasons I won't go into.
Yeah, this is what I thought. I mean, it's just the mathematics of it. But you're traveling back in time. It has physical component, not just math formalism. Yeah, I understand. Thank you.
Yes, exactly.
Thank you, Doctor. Would you like to make any closing statements before we say goodnight?
um, yeah, so I mean, thanks again for inviting me. It was a lot of fun. Definitely got a lot of interesting questions from the audience. And, I invite everyone to read my papers on the subject. I have one of them is lecture notes. So these are kind of advanced physics intended for fourth year physics undergraduates. But if you don't know that math, so I can see some people here do know that math, but if you don't, you can just skip the math and just read the words, and that should be good enough. And also have a paper about two papers about tantral paradoxes, which are papers where I show that Novikov's conjecture doesn't solve this particular paradox, but multiple histories do solve it. And these are, I think, a lot more readable to the general public. And there's going to be two more papers. Maybe I should also mention my students. So my student Jacob Hauser is the one I wrote the first paper about tantral paradoxes, and then later wrote another paper on the same subject with another student, Jared Rogan. and now I'm working on what I mentioned before, on warp drives in 5 dimensions with my student Alicia Savelli, and that paper is going to be out hopefully within a month or so. So, if you keep track of my website, it's going to appear in my publications list on my website. And generally, I think the best place to start if you want to know more about this, from at least from my point of view, is my website, where I describe this research in kind of general terms, and I describe more specifically what I did and what my students did, and link to all of my papers and so on. So you can go there. You, if you can maybe share the address to that, that would be nice. The address is just baraksh.com, or you can just Google my name. You should also follow me on Twitter, which is where I post most of my musings. Some about time travel, but mostly just stupid puns and dad jokes. And yeah, I'm happy to talk about this stuff, and I'm happy that people find it interesting, and I welcome you to learn more about it.
Thank you so
All right.
much. We had the paper of the lectures posted up here, and now I put your websites up. Please check out the website and follow Barak on Twitter. It's a really great source of knowledge. And yeah, we thank you so much for taking the time and talking about your very interesting work. And yeah, it was an amazing talk and discussion, and we are very thankful for that. And please come back anytime. Maybe also
Yeah,
with
we
your
hope you can come back last
yeah.
week.
Please let us know what we have to do so you come back. Basically, I was already asked that. Katerina, what do we have to do so he will come back? So we are open for suggestions
We need to
from your
find him a
side.
leader of antimatter.
Yeah.
And Jamie reminds me, so on your website, are there time travel jokes? Is that what we can expect if you come back next time?
That's on my Twitter, but yeah, I'll see you guys last month, and
Thank you so much, Doctor. Thank you so much.
And thank you everyone for participating so actively, for asking questions, for chatting in the chat. This was such an amazing chat all around. And yeah, so this definitely sparked more interest. And yeah, please come back anytime. And if you like this room and rooms like this with guest speakers, follow the club. We'll have more guest speakers coming here next week.